Hi, in this video, we'll be talking about linear independence. So, in the previous video, we have talked about the span of a vector space, and now we want to talk about whether a subset is a linear independent set or not. So, what does it mean? Well, we define linear independent if there exist distinct vectors and scalars, not all zero, such that this linear equation is consistent. And a set that is not linearly dependent, it will be then known as linearly independent. And so, it is saying that linearly independent is that for all these distinct vectors, if this linear equation holds true, then all the scalars must equal to 0. That's what it means to be linearly independent. And a few consequences of this definition is that any set which contains a linearly dependent set would then be also linearly dependent. Because you just imagine now you have a bigger set with, but here is like, here's this part is the linearly independent part maybe, and this part is linearly dependent already that you know. Then this part will be the non-zero part portion, then everything here can be 0. So it still be overall non-zero, not all 0. So any subset of a linearly independent set will be linearly independent as well. So if you have lesser vectors inside a linearly independent set, it will of course be linearly independent. And any set which contains the 0 vector is linearly dependent, because you can just multiply any scalar in front of the 0 and you'll still be 0. And the set of vectors is linearly independent if and only if each finite subset is linearly independent. So this gives us a new way to define linearly independence for infinite sets. And an exercise for you to show is that if X is linearly independent, and now you take Y being an element of V, complement away the span of X, then X union this element Y will still be linearly independent. And it's not really hard to see, because Y cannot be written as a linear combination of any one in X. And so when you add it together, Y is not a linear combination of this. And so you can imagine that you want to find what scalars holds true, then it must be all 0. Because when you equal 0, you just bring the Y over, then for this equation now to hold true, all the scalars must be 0 equals to 0. So that's the gist of the proof. You can write it out more rigorously if you want, but I hope it is quite intuitive why this is true. And because of that, we will have a theorem, and if you have some linearly independent vectors, and if UK plus 1 is not a vector of Rn, and is not a linear combination of this, then this U1 to UK plus 1 will now be linearly independent. And that is basically this exercise over here, but this is for a general vector space. And you can see the proof of it is very straightforward. You just take a vector equation, and then we will first show that the CK plus 1 can't be 0, because if you assume that it is non-zero, then UK plus 1 can equal to a linear combination. So it must be 0, and then when you get this part to be 0, you show that everything else is 0 as well. Hence the only solution is if C1 to CK plus 1 are all 0. And this means that U1 to UK plus 1 is linearly independent. So this is for the Rn case, but it's really just, you can easily generalize it by just removing this Rn and put V. Now we have a proposition, is that if you have a non-empty subset of a vector space, then X is linearly independent if and only if every element of the span can be written uniquely as a linear combination in the span. So if X is linearly independent and you have two linear combinations that equal to the same vector, then when you bring over, you can minus off, and because they are linearly independent, all these coefficients must be 0. And for this to be 0, it means L1 must equals to alpha 1, hence showing that the vector is unique. And if the vector expression is unique, then of course, C1 plus all the way to Vn equals to 0 can also be written as 0 plus all the way 0 V1 plus all the way 0 Vn. And because it's unique, this must be the only possible linear combination. So C1 plus all the way is 0, hence X is linearly independent. So this shows that linearly independence allows us to write elements uniquely in the span. And this will be the idea in the next video where I talk about the basis. And so we say that an element is redundant if the span of X can equal to the span of X minus away this element X. And if this is so, then V is an element of the space, then S union V equals to S, meaning V is redundant if and only if V can be inside the span. And we already know why this is true, in a sense, because we have already proven this. X union Y will still be linearly independent. So if you think about it, we shall just prove it quickly. If V is not in the span, then the sets will not be equal, since V will of course be an element of S union this. So now to prove the other direction, you assume V is in the span. So V can be written as a linear combination. And we can just show the mutual containment, because of course S must be contained inside this. For the other side, if you take any element in here, because W is a linear combination of this, we can write it as this. But V is a linear combination of this, so now it just reduces to a linear combination of S1 to Sn. And so W will be in the element of the span of S. Hence, this shows that both containment holds true. This means that S union V equals to S. Hence, we have proven this lemma. And so, if you just negate both sides, we say that a subset is linearly dependent if and only if it contains some redundant vector. And a corollary will be that S is linearly independent if and only if V it strings the span properly. So that means S minus away this V cannot equal to the span of, will be properly contained in the span of S. So that's what it means for S to be independent. And the proof will just follow, because if S is linearly independent, then none of the vectors can be written in the form of each other. So a removal of any vector will of course string the span. And if S is not linearly independent, then it contains a vector that is dependent on the others, and so you can just remove it and it will still hold true. Just take this lemma to use. So this gives us an intuitive definition now that a spanning set is minimal if and only if it is linearly independent, meaning you remove away all the redundant vectors. And next, we show that a vector space, any finite set has a linearly independent subset with the same span. So for a finite set, you just take this, and it will be linearly independent. If it's linearly independent, then S itself satisfies the statement. So we assume that it's linearly dependent. Then you can just find the vector that is a linear combination of the others and remove it, and it'll still be the same span. And if it's linearly independent, then we are done. If not, you can just do the same process where you find the vector that is a linear combination of all the others and disregard it. And you can keep doing so because it is finite. And in the end, even if it ends with an empty set, it will fulfill the condition that it is linearly independent. So the idea is that you throw away the redundant vectors from any spanning set. So let's just look at a concrete example to familiarize ourselves with linearly independence. And we just take this example in R3 and we'll show that this set is not linearly independent. So how do you calculate that? Well, you first form a linear equation as follows, and we just form the system of linear equation next. So and once you solve for this system, then you see that the solution set is as the following. And if we set C5 to equal to 1 and C3 to equal to 0, then we get this linear equation to hold. And so this shows that this set is not linearly independent already. And so with that, this shows that the vectors from S that we associate with C5 is in the span of the set C1 and C2. So we can disregard the fifth vector without shrinking the span. And similarly, setting C1 to equal to 1 and C5 to equal together, we should ensure that we can disregard the third vector as well without shrinking the span. So thus the set has the same span as the following. And now we can check this is linearly independent. Hence, we have used what we have already known as Gaussian elimination to help us find redundant vectors and remove them, and also show whether a set is linearly independent or not. I hope you have understand what is linearly independence now, and in the next video I'll be talking about basis, so stay tuned. Bye.